In this video, I'm going to go through kind of some of the additional theorems related to polynomials and roots, and then including multiplicities, and then get to a conjugate roots, so complex roots. So the fundamental theorem of algebra, so it's a lot of jargon here, but just to explain what it means, what it tells you is that every polynomial, and if it has, whether it has real or complex coefficients, it has at least one zero. It means that if there's a number that you substitute here, that would give you an answer equal to 0. So you at least have 1 0. It means you at least have one factor in this. And this 1 0, at least 1 0, could be a complex number. So if I substitute this complex number in here, then it's equal to 0. Remember that if I say something belongs in the complex number, it means that it could be a real number as well. So the complex number holds all the numbers, but at least with the fundamental theorem of algebra, we're saying that whether it's real or complex, the polynomials have at least 1 0. So as a result of this, we create what we call a lemma. So it's a result of this. It means because I have a 0, it means I can use these zeros to factor my expression. It means that each polynomial, whether it has real or complex coefficients, every polynomial with real coefficients can be written in factor form. And the factors that you have inside are belong in the complex numbers. So again, they could be real, they could be completely complex, as in they have imaginary parts. So one of those options. So this is just to tell you that polynomials have factors. It's not like the factor and remainder theorem where you can actually apply it, but it is something that you're gonna that is just useful to know as a fact. So one thing to note as well is something called multiplicities. Multiplicities comes from the word multiple, so it tells you just sometimes you get a repetition of powers. I don't have the theorem down, the fact written down here, but what it tells you is that in simple expressions, that the number of powers you end up getting in your factorization should be equal to your polynomial, the degree of your polynomial. So, for example, if I have an x squared plus x minus 6, this is going to give me x minus 2, x plus 3. This is an x minus 2 to the power of 1, x plus 3 to the power of 1. If I add the powers, it's going to give me the degree of my polynomial. Remember, the degree of the polynomial is the degree of the highest power you have. The degree of this polynomial is 2, and 1 plus 1 is obviously 2. So when is this useful? Sometimes I have a repetition of powers. So say, so let's say I have x squared plus 10x plus 25. This is a perfect square, so the factorization is actually x plus 5 squared. So again, this has a degree of 2, and this I have a total power of 2, and they should add up. So sometimes you'll get something like x cubed plus x squared, something, and you'll end up with, for example, I'm just bringing a rough example, and an x plus something, a p. Again, this is a degree of 3, and the powers here will add up to 3. What we say is that x plus 5, as the factor x plus 5, has multiplicity 2. And in here I say that the factor x plus 1 has multiplicity of 2, and the factor x plus p has multiplicity of 1. So just multiplicity tells you how many times does it repeat as a factor. Let me go through one example about this. So say I have say I have f of x equals to 2x to the power of 5 plus 7x to the power of 4 plus 3x cubed minus 13x squared minus 17x minus 6, quite a long polynomial. So with this, the degree of this polynomial is 5. What this tells me is that if I end up factorizing, say, x plus q, x plus alpha, I'm just picking random numbers, and then I have the powers, so say n1, n2, n3, the powers should add up to 5. I should have 5 factors in total. So that's a consequence of the lemma that we went through on the first slide. So if I tell you that this function has a -1 as a 0 with a multiplicity 3. Now this means two things. One is that that's the expression x plus 1, remember you reverse the power, x plus 1 divides my f of x 3 times. So I can divide f of x by x plus 1 3 times successfully. And then because so I can rewrite f of x as x plus 1 cubed, and then I'll have two more expression, or one expression to the power of 2, as long as the powers will add up to 5. Now, if I know this fact, and they tell me express f of x as a product of linear factors, we can use this fact to be able to find the other factors. So in the beginning, you're like, well, this is to the power of 5. How can I end up reducing it to linear factors if I only know one root? Well, this one root has a multiplicity of 3, which means I can use synthetic division 3 times. So let's go through that. If I try synthetic division with a -1, so I'm going to go 2, 7, 3, -13, -17, and -6. And then I am doing synthetic division by a -1. So doing this really quickly, 2 goes down, -2, add these together, 5. So we get -6, and we have a 6 and 0, which is what we're meant to get, because the remainder should be 0. So we've divided it once, but we have to repeat the process again. So using the same expression, we don't have to go too far, just rewrite it down. And again, we're dividing by -1 because we are allowed to do -1 3 times. So this is 2, we have and 6, and again 0. And for the third time, we're going to take the last expression. We have 2, 3, -5, -6, and -1. So and we get a 0, which is what we're meant to get again. So we are left with this expression. It means that f of x is equal to x plus 1 cubed, because we just divided 3 times. And then we have this, and remember you start with your constant, so -6, and then I have x here, and then I have 2x squared. So surprise, surprise, I'm left with a quadratic, and I should know how to factorize a quadratic. So the factorization of this quadratic, which I'm not going to go through, is going to be 2x minus 3 and x plus 2. So this is how you use the fact of multiplicities. It's also how you can use one of the factors to be able to find the other factors. It's also how you can use synthetic division multiple times. So this example just encompassed a lot of different facts in here. So hopefully this was useful. And another video, so this is part 2 of this video, where I'm gonna go through the conjugates and complex roots.